Hi class, I'm making this video to help you prepare for the exam and for the final exam, just to make sure that you understand more or as much as you want to about the context-free languages and especially the pumping lemma that goes with the context-free languages. First, let's do some definitions. I need you to understand the difference between a context-free grammar and a context-free language. A context-free grammar, those are the only really kind of grammars that we've seen so far. In a context-free grammar, the rules are structured so that they replace a single variable or non-terminal with some replacement text. And so all the rules have a non-terminal getting replaced by something. In non-context-free grammars, you don't just replace non-terminals, you can replace an entire phrase out of a working string that has terminals and non-terminals in it with another phrase. So that's not the kind of grammars we're talking about here. In context-free grammars, you're just replacing a single non-terminal with stuff. Now, what's a context-free language? That is a language for which you can make a context-free grammar, or alternatively, a push-down automaton. Now, I want to show you my little trick. This just sort of helps you see what you think a language is, whether it's context-free or not. This is not a proof either way. If you want to prove a language is context-free, you have to find a grammar for it or a push-down machine for it. So this is just a feeling. If you want to prove a language is not context-free, then you have to use the pumping lemma. But let's just do this bird's foot trick. The way this trick works is that you draw lines connecting groups of letters that have a variable in common or a relationship in common. So here we've got the same variable occurring twice. We would draw lines connecting that. And I call what we make here a bird's foot. This is the whole foot and these are the toes. So here are the rules of thumb for when a language is context-free and when it's not. So here are the rules of thumbs, and I scribbled a little bit here and wrote a language beside the rule that illustrated the use of the rule. First rule is if a foot, one of your bird's feet, has 3 or more toes, then the language is not going to be context-free. And that happens when you have a language like A to the N, B to the N, C to the N, where you have 3 uses of the same variable. You see this bird's foot has 3 toes, and that language is not going to be context-free. If you have a language like this one, where the toes of 2 different feet crisscross, then the language is not going to be context-free. And you see that here's one foot drawn for the A's and the C's because they share that N variable. And then here's another foot drawn for the B's and the D's because they share the M variable, and the toes crisscross. Now, if you think about these things from the point of view of a stack, then you see how this toe drawing business helps. If you are processing a string in this language, you would have to remember the count of your A's, so you have to push them. And then you have to use that count when you read the B's to make sure the numbers were the same. So you have to pop an A for every B. But now your stack's empty, and you still have to read the C's and make sure they were the same count as the A's and B's, and that's not going to work out. Using a stack here, you would have to push these A's because you have to remember their count for when you get down here to the C's. And you would have to push these B's so that you could remember their count for later. But then when you get to the C's, your A's that you need are buried below the B's. And you can't get to them without destroying the count of the B's. So that doesn't work out. Now the total number of feet that you draw doesn't matter. It just matters that they are properly nested and they each only have 2 toes. So here's a little drawing that would tell you that the language was context-free. If you had this one nested inside the outer one and then 2 in here and another one out here, that'd be fine. This drawing also tells you how to use your stack because when you're on the left toe, you're going to be pushing, and when you get over here to your right toe of the same foot, you're going to be popping. So this would tell you that whatever letter group was there, you'd push, then you'd push, then you'd push, and then you'd pop. Then you'd push and pop, and then you'd pop, pop, and then you'd push and pop. So that's kind of a useful little picture that we need. Let's look at this list of context-free languages, just so you have this nice list that you can put on your cheat sheet. The first language we have here is equal. Notice there are only 2 letters in our alphabet. If you just have 2 letters, you can do the language equal as a context-free language. Palindrome is context-free. We've seen grammars for both of these, and we've seen push-down machines for both of them, as we have for this language, where you have NAs followed by NBs. Now let's use our bird's foot trick on this one right here. Here's a superscript N, and way down over here is another superscript N. So let's connect those. Here's an M and an M, so connect those. There's no more N's and there's no more M's, so each of our toes, each of our feet so far has 2 toes. This foot only needs 1 toe because it's a standalone. There's no other P's anywhere, and there's no other Q's anywhere. So this is a context-free language. And to recognize this language with a stack, you would push, then you would push, then you'd pop off these for each of these, and then you'd pop off these for each of those. So when you get here, you're popping. And then when you only have 1 toe, you don't even use your stack. You just read and you read. Now let's take a look at this one down here. Here we have I, K, P, and Q. So are they all separate and not related? If we look over here, we see no, that's not the case. I plus K has to be equal to P plus Q. So these are being treated as a single value here and compared to this single value. So what we have is this group treated as a unit and this group treated as a unit. So when we draw our bird's foot, we only have 2 toes, and that's not going to be a problem. How would we recognize this language with a stack? Well, we would push all of these, and then as we read these, we would pop these off. The C's don't have to always pop off B's. You could have A's being popped off for C's if you wanted to. There's no relation between P and I directly, or P and K. It's this sum related to that sum. Now, a little word of warning. If that was a multiply operator, this would not be context-free. So this only works when you're doing addition. Let's look at a list of languages that are not context-free. Look at this one right here. You've got 3 letters in your alphabet. You cannot make sure that 3 letters have the same count. So this language is not context-free. And we've seen that double word is not. The problem with double word is that a stack reverses things, and so when you push the first word onto your stack, it's now in reverse order as you pop it off. But double word has 2 words that are the same exactly in forward order, so that doesn't work with a stack machine. Here is the language that has 3 counts that are in the A's first, B's then next, and C's last order. That's a subset of this one. This is not context-free. Here we have one where the toes crisscross. There's a P and a P, and then there's a Q and a Q. And I just threw these in to give you a little bit of insight past the languages that are specified with those superscripted variables. If your string lengths have to be powers of some kind, powers of 2 or powers of 3, or if some count, like if your count of A's has to be a power of some kind, that is not a context-free language. We need a Turing machine to recognize those, and prime is even harder than powers, so we need a Turing machine to recognize strings whose lengths are prime or the number of A's is prime. Now, if you want to show that a language is context-free, what you have to do is find a stack algorithm or a push-down machine for it, or find a context-free grammar for it. That little trick that I just showed you with the bird's feet gives you a clue that it's going to be context-free, which makes you keep looking for the context-free grammar or machine for it. But it is not a proof. If you want to show that a language is not context-free, now you have to use the pumping lemma. You can't just do the opposite of how you show it is context-free. You show it is context-free by finding, let's say, a context-free grammar. Well, you cannot prove that it's not context-free by not finding a context-free grammar. That doesn't make any sense. So you have to use this pumping lemma, which is what we need to talk about now. So here's a very simple statement of the pumping lemma. If you've got a language L that's a context-free infinite language, and you've got a string W in L that is, in quotes here, long enough, without specifying exactly what that means now, then you will be able to find two cycles in that string W that you can duplicate 0 or more times. That's what we call pumping, and you have to do each cycle the same number of times. And all the strings you make by doing that will also be in the language. That's the simple statement of the pumping lemma. Here's the formal statement. If you have a context-free grammar that's in Chomsky normal form, remember what Chomsky normal form is. You've got non-terminals getting replaced by two non-terminals, or non-terminals getting replaced by terminals. If you've got that kind of grammar, and that grammar has P live rules, those are the ones with two non-terminals on the right side, and you've got a string W that this grammar can generate, and that string W has length greater than 2 to the power of the number of live rules that you have, then you will be able to take that string W, because it's long enough, and break it up into 5 pieces with these restrictions on the pieces. That piece that you call X can't be empty. The pieces that you call V and Y cannot both be empty. And the length of the string that goes from the beginning of V to the end of Y can't span any more than 2 to the P letters. Now, once you've broken that string into your 5 pieces, you can duplicate V and Y n times, where n is greater than or equal to 0, and all of the strings that you make can also be generated by that grammar. So in other words, they are also in your context-free language. Now to prove this, we've got to work. So let's get started on that. First, we need to remember what are live rules and dead rules. I just said. Here are the two kinds of rules that you get in a Chomsky normal form grammar. Non-terminal gets replaced by two non-terminals or by a terminal. These rules up here are called live rules because they keep the derivation going. And these rules are called dead because once you've replaced a non-terminal with a terminal, that part of the working string is finished. There is a relationship between the length of a string that you can make with one of these Chomsky normal form grammars and the height of the tree that makes that string. And we worked out that relationship in class. Let's review. Here are some trees. This is what they look like. You see these, when you replace a non-terminal with two non-terminals, you get a node with two children in your tree. When you get ready to replace a non-terminal with a terminal, then you only get one node for that, and that is going to be a leaf because that's a terminal now. So this is the shape that your trees have. And this shape of a tree gives you a relationship between the number of leaves that you have in the tree and the height of the tree. And here was the way we wrote down our discovery about that relationship. That a string that's longer than a power of 2, where I is the power, requires a tree of height greater than I plus 1. So it's putting this to work with actual constants. Let's use I equals 3. A string with length more than 2 cubed, 8, would need a tree of height more than I plus 1. 3 plus 1 is 4. So let's pick a number larger than 8. Let's pick 9. A string of length 9 needs a tree of height at least 5 because it has to be more than 4. Now let's draw a little tree. Okay, there's a tree. Now I would like to count on the longest path in this tree how many live rules were used. And by the way, the length of the longest path in a tree is the height of the tree. That's the same thing. So here's a longest path. There's actually two of them, the same length. And how many live rules were used along that path? Well, there's a live rule. That's 1, 2. And why I'm counting is because these nodes have two children. 3, 4, 5, and this only had one child, and that didn't even have any children. So to make this path right there, we needed 5 live rules, and the path has length 1, 2, 3, 4, 5, 6. So that's where we get this relationship up here. If a path from root to leaf has length n, then n minus 1 live rules were used to generate that path. So you remember in the pumping lemma, we had this 2 to the p thing going on. Why is that important, and where does it come from? Let's step through this slide. This is a real important slide to understand. P is the number of live rules you have in your grammar. Our relationship that we found between string length and height of the tree says if a string has length greater than 2 to the p, then its tree is going to have a height greater than p plus 1. We just substituted p for whatever variable we were using. I think we used I before, but we just stuck p in there. So if a tree has height greater than p plus 1, then the shortest such tree would have to be height p plus 2. So we could rephrase that as if a string has length greater than 2 to the p, then its shortest tree would have to have a height p plus 2, because it has to be greater than p plus 1. And remember from our discussion on the previous slide, a path of length p plus 2 would require p plus 1 live rules. But there are only p live rules in the whole grammar. Therefore, some live rule had to be used more than once. Remember the definition of self-embedded? A self-embedded non-terminal is one that occurs at least twice in a tree where one of the occurrences is a descendant of the other. If that's the case, then the non-terminal is said to be self-embedded. And when you make a string longer than 2 to the p, and you force the use of some live rule more than once, then you get a self-embedded non-terminal. It's the non-terminal that belonged to the rule that you used more than once. Now you remember these things that I call tents. When you find a self-embedded non-terminal in a tree, then you use that non-terminal and you draw these tent things in the tree to help break that string up into 5 parts so you can see where the cycles are and what happens when you pump. So let's practice. This is awfully small. I hope you can see it. Alright, in this tree over here, there's an S at the very top. There's an S there, an S there, and an S there, all on the same path. Now I can take any 2 of those S's and use them to break my string up into 5 parts. The breakup of the string will be different, but all of them will work equally well and will make a correct string for pumping. So let's see. Let's take this right here. You have to be careful not to grab something that doesn't belong in the subtree that you're supposed to be surrounding. So I've got to be careful and work my way around these things. Alright, there's my 2 tents. Notice I drew a tent just above the top S and just above the bottom S, and I included within the walls of that tent everything that was descended from the S I picked. Now, this breaks the string that the tree made into 5 parts. The stuff out there, the stuff in between those walls, the stuff in the middle tent, the stuff in between those walls, and the stuff out here. This is U, what we call U. This is the stuff we call V. This is X, whoops, X. This is Y, and this is Z. and V and Y are the two cycles. Now here is a little line I'm supposed to be writing according to, this is on one of your worksheets, supposed to write the part of the string that was U and V and X and so forth. So let's look. The stuff out here is A and B. So this part of the string is AB. V is just A. X is AB. Y is just B. And Z is AB for those particular tints. So now, when I pump, I duplicate V and Y the same number of times. If I pump one time to put in 2 copies of each, then the string I make is going to be U, V, V. So that's one A and another A. Then X, that's AB. Then Y, Y. So I get B, B. And then Z, which is AB. So that's the string I would make if I pumped one time. And if we wanted to take time, we could see, this is the grammar that the trees are drawn from, we could see that you could generate that string using the grammar. What you would do is when you got here in your derivation process, you would not replace S with AB like you did. You would replace that S with AC, and then you'd replace that A that you made with this A, and the C that you made with SB, and you just duplicate at this S what you had done at that S before, which would make you a third S that had this X as its descendants. I hope that makes some kind of sense. Let's go over here and pick C. There's C self-embedded in this tree too. Let's pick C and just do this one more time. So there's the tint around the top C, and here's a tint around the lower C. And this breaks my string up into A for the part called U, BA for the part called V, ABB for the part called X, AB for the part called Y, and Z is empty. U and Z are often empty. If you pick the starting non-terminal as the top of one of your tints, then both U and Z would be empty. Alright, so now when we pump one time, we'll get A, that's U. Then we'll get V twice, that's BA, BA. Then we get X, which is ABB. Then we get Y twice, AB, AB. And then Z, which is nothing. That's going to be a legal string in this language too, and the way you would generate it is to do at this C what you did at that C. And then you'd produce this third C down below. Now let's restate that pumping lemma to see if it makes any more sense. This is just the same thing we saw before. If you've got a language G, or sorry, grammar G, that's in Chomsky normal form and has P live rules, and you've got a string W that has length greater than 2 to the P that grammar can make, then you can break that string W into 5 pieces called these names U, V, X, Y, Z. The restrictions on them, which we didn't really deal with, but just take it on faith, the restrictions are that X is not going to be empty, that your 2 cycles V and Y are not both going to be empty, and that the length of the string from the beginning of V to the end of Y is no more than 2 to the P, then all words that you can make by pumping up V and Y n times where n is greater than or equal to 0 can also be generated by G. So now let's use this lemma. We always do that the same way. We use this lemma to prove that languages are not context-free. We start out by assuming that they are. And because our assumption says they are, then that must mean that the pumping lemma is true for that language. The pumping lemma says that if you get a string longer than 2 to the P, you'll be able to put 2 cycles in it and pump, and you'll make only good strings. So what we have to do in our proof is find a string that's longer than 2 to the P and argue that there is no place at all in the whole string where you could put your 2 cycles that would not produce incorrect strings. There's no place to put the cycles that would actually work. And we have to go through the whole business about where all could you put the cycles. We have to exhaustively show that you can't put them anywhere in order to have a correct proof. So here's an example. This is for the language A to the N, B to the N, C to the N. That is not context-free, and here's a proof of that. We are going to start by assuming that it is a context-free and that therefore the pumping lemma applies. And then if we felt like it, we'd state what the pumping lemma says. But since we all know what the pumping lemma says, it's okay with me if you leave that part out and just go straight to this part. Well, consider the string. Now you have to pick a string that has at least 2 to the P letters. Pick the string 2 to the PAs followed by 2 to the PBs followed by 2 to the PCs. It was hard for me to write that in PowerPoint because I didn't know how to stack superscripts 3 tall. So let me write it by hand. So here's what I'm talking about. You have 2 to the PAs followed by 2 to the PBs and 2 to the PCs. And now we have to show that there is no place to put 2 cycles that would allow us to pump and make correct strings. So the first thing this proof points out is you can't put the cycles across a boundary. What I mean is you can't grab some A's and some B's in your cycle, because let's say you did. Then you've got all the A's that made up U, and then you've got some A's and some B's in your V, and now you're pumping, so you're getting V twice, and look what's happened. You've got A's, then B's, then A's, then B's. That's not allowed. This language has all the A's first and then all the B's. So you can't grab both A's and B's in your cycle, and similarly, you can't grab both B's and C's in your cycle. So you have to put your 2 cycles completely, each within one group of letters. Now, if you put 1 in the A's and 1 in the B's, then you're leaving out the C's when you pump, and all 3 letters are supposed to have the same count. You cannot keep 3 letter groups all having the same count with just 2 cycles. It's impossible. And that's what you say. That's your argument. And then that forms a contradiction to your assumption that the pumping lemma is true. And that was based on your assumption that the language was context-free. And therefore, it cannot be context-free. Let's do another example. All right, here's double word. Double word's not context-free, so we assume that it is in order to prove that it's not. And we pick this particular string. 2 to the PAs, 2 to the PBs, then 2 to the PAs and 2 to the PBs again, because it's a double word. Now, if we could put a cycle here and here, then when we pumped, we could keep the A's in both words the same, and it'd still be a double word. So you have to say why that's not possible. And you fall back on this part of the pumping lemma that says from the beginning of your first cycle, which would be in here, to the end of your second cycle, which you would like to be over here, you can have no more, less than or equal to, 2 to the P letters. But look, there are 2 to the PBs between those 2 groups of A's, so that's impossible to put your cycles there and there. And likewise, it's impossible to put a cycle there and a cycle there. They're too far apart. So you'd be restricted to putting your cycles in letter groups that are right next to each other. But if you put them here and here, then that doesn't work out because you're not changing this word, and it's supposed to be a double word. You can't put them here and here. You can't put them here and here. You can't put both cycles in these A's. You can't put both cycles in these B's. There's just no place to put 2 cycles in this double word, since we know that you can't put them where you'd like to put them. There's no other good places to put them that keeps the string a double word when you pump. Let's do one last example. Let's do one last example, and this is a problem that you had in a homework. This language has NAs followed by JBs and then PAs and QBs. But there's a relationship that has to be maintained between N and P and between J and Q. What this says is that in this group of A's you can't have any more letters than you have in that group of A's. So the first group has to be smaller than or equal to this second group, and that's true for the B's as well. So here's a string that makes use of the equality relationship between the number of A's here and here, and same for the B's. It's okay if they're equal, and that's what this string has. Now, if you could put your cycles in this group of A's and here in this group of A's, and you pump the say you had equal size cycles and you pump the same number of times, well, that would maintain your relationship and it'd be okay. You'd make good strings. But as with double word, those are too far apart. You can't put your cycles there. And you can't put your cycles in the B's either. That's because of this. So where could you put your cycles? Well, you could put them in groups that were next to each other. But if you put them out here, either both in the A's or both in the B's or one in the A's and one in the B's, and you start pumping, then this part of your string is going to grow long, and this part isn't going to change, and it's going to foul up this relationship. So then you say, okay, so you can't do that, but why can't you do this? Why can't you put your cycles down here in this part of the string? Because if this gets bigger, that's no problem. Well, you then have to rely on the idea that when you said you were going to pump using N copies of V and Y, you remember that? What was the bounds on N? I can't get that to make a dot. Okay. N had to be greater than or equal to 0, which means if N is 0 that you can take these cycles out. Take them out completely and still have a good string. That's what the pumping lemma tells you. Well, so suppose you put your cycles out here. Now these letters all have the same counts. This group of A's is exactly the same count as this group of A's. If you put a cycle here and then you take that cycle out, then this group gets smaller than that group, and that fouls up the string. Same for the B's if you put the cycle there. So that's the argument that you need for this particular language. What changes from one example to another is the string that you pick. You can pretty much always throw 2 of the P's in there and pick a decent string. But what really changes is your argument of why you can't put cycles in any place in the string that you picked. That changes depending on what the specifications are for the language in question. Okay, I hope that helped. That's the end of this video.